Welcome to this talk, which is part of the Static Analysis Symposium 2020. My name is Marcel Hark and I'm from RWTH Aachen University, and I'm going to present our paper on the decidability of termination for polynomial loops, which is joint work with Florian, Frohn and Jürgen Giesl. What are we going to study in this talk? We are interested in so-called universal termination of programs, which is one of the most important liveness properties. For example, it ensures total correctness of programs. However, termination of general programs is of course undecidable, which was first shown in Turing's groundbreaking result in the 1930s. Thus, there can be no technique which can prove or disprove termination for all kinds of programs. Still, we can hope for finding subclasses of programs where termination is indeed decidable. And this has already been done for so-called linear conjunctive loops. Such a linear conjunctive loop has a loop condition which consists of linear inequations, which can be strict or non-strict, which are connected via conjunctions. And the update is basically the multiplication with a matrix. If the entries of this matrix A, the matrix B, and the vector B are from the real algebraic numbers and the variables range over the real algebraic numbers, decidability was shown by Tivari in 2004. Braverman established this result over the rationals in 2006. Then for the integers, this result turned out to be actually harder, and after a few partial results, Orknin and his colleagues were able to prove decidability over the integers in 2019. Still, we can ask the question, what about nonlinear behavior in the condition or the update? And in this talk, we are going to study so-called triangular weakly nonlinear loops. Consider just a polynomial loop with some condition phi and some update x. Then for the decision procedures in the linear case, it was crucial to be able to compute a closed form for the iterated update. And here we restrict ourselves to these triangular weakly nonlinear or TWN loops, since they admit such closed forms. A triangular weakly nonlinear loop looks as follows. The condition phi, depicted in yellow, is built from the logical connectives and or. It can also contain negation, but negation is just syntactic sugar here, since we consider polynomial inequations over the ring S. The coefficients are also from S, thus the variable value depends at most linearly on its previous value, which prohibits super exponential growth, as for example in x1 is set to x1 squared. Also, the polynomials pi are polynomials in the variables xi plus 1 to xd, thus the variable value depends polynomially on previous values of variables with higher index. And this then prohibits circular dependencies. S is a ring somewhere between the integers and the real algebraic numbers, and this is where the coefficients are from, and the variables range over s to the power of d. This encoding gives us a framework in which we can analyze termination over the integers, over the rationals, and over the real algebraic numbers. An example for such a TWN loop is depicted in the upper right. As long as x1 plus x2 squared is greater than 0, as x1 is set to 1 times x1 plus x2 squared times x3, x2 is set to x2 minus 2 times x3 squared, and x3 is set to x3. So the coefficients ci are all 1 here. P1 is x2 squared times x3, P2 is 2 times x3 squared, and P3 is 0. Our contribution is then that termination is decidable when the variables range over the real algebraic numbers, and non-termination is decidable for the integers and the rationals. We can generalize this result to certain non-TWN loops and also give tight complexity results on the decidability of termination in case of linear updates. This talk is organized as follows. After the motivation which I have just given, I will explain how we use these closed forms and how these closed forms then enable us to reduce termination to this logic, which I will present later on. I will then show how we can generalize our results to certain non-TWN loops, and I will report on the complexity of deciding termination thereafter. Finally, I will conclude my talk. So what's the general idea? The general idea is, given such a loop, compute a closed form of the update. And this closed form then depicts the values after n iteration expressed in the initial values. Thus, if we replace the variables by the closed form, so we take the condition, replace the variables x by their closed form, and then is there some x such that for every natural number n, this holds, is the same as saying x witnesses non-termination. For our TWN loops, the closed forms are so-called poly-exponential expressions, and even more important, these closed forms are indeed computable. So for the example loop which I showed to you in the beginning, the closed form is given by this vector. As x3 never changes, its closed form is x3. x2 is decremented by 2 times x3 squared, but x3 squared of course never changes throughout the loop, and this is why the closed form is just x2 minus 2 times x3 squared times n. The closed form for x1 is then a bit more involved, since x2 indeed changes, and we have to and we of course have to take this into account when computing the closed form for x1. Now we can see that when collecting the coefficients of these powers of n here, then we basically obtain a polynomial in n whose coefficients are polynomials in x. And this is why these expressions are called poly-exponential. Why exponential? If we would have another variable x4, which is doubled in every loop iteration, then its closed form would involve this 2 to the n times x4, so this exponential part here. Now, given the closed forms for x1 and x2, these variables also appear on the left-hand side of the loop condition. Thus, if we insert the closed form into the condition, we obtain this expression, and the ultimate truth value of the condition after n iterations is determined by the ultimate sign of the expression. Thus, this expression determines whether an initial assignment eventually witnesses non-termination by its sign, which it eventually has. This is useful since for polynomial loops, eventual non-termination is the same as non-termination, where eventual non-termination means ignoring a finite amount of loop iterations. We then have non-termination, meaning that the condition holds after finitely many steps forever onwards. Now this idea can be used to reduce termination to a logical theory which is depicted by this symbol. And this is the theory which is the existential fragment of the first order theory over the ring S and the real algebraic numbers, which consists of Boolean formulas of polynomial inequations with coefficients from the real algebraic numbers, where the variables can be existentially quantified over the ring S or the real algebraic numbers. So the variables can especially arrange over the integers, the rationals, the real algebraic numbers, or even the real numbers. An example for a formula which is in the existential fragment of the integers and the real algebraic numbers is there some x3 in the integers such that 4 over 3 times x3 to the power of 5 is greater than 0. But this is nothing else than asking is there some assignment for x3 such that the coefficient of n to the power of 3 in this expression is positive? Thus, checking whether the ultimate sign is 1 of this expression can be reduced to this theory. And this works as follows. We can order the terms in this expression with respect to their asymptotic behavior in n. For example, whenever x3 is assigned to a non-zero value, then no matter what the values for x1 and x2 are, this term will dominate the whole expression, and eventually this expression will have the sign of this coefficient. So if this one's positive, then this expression is eventually positive. If this one's negative, the expression is eventually negative. So we can give a formula for positivity of the dominant coefficient. If alpha 1, the red term, is greater than 0, eventually this expression is positive. If alpha 1 is 0 and alpha 2 is greater than 0, alpha 2 is the dominant term and the expression is eventually positive. Now the same holds if alpha 1 and alpha 2 are 0 and alpha 3 is greater than 0, and also for alpha 4, which is the yellow term here. Still, we need to existentially quantify the variables over the ring S, since we are interested in termination of the ring S. So what have we done? We have taken this expression and given a formula which reflects whether this expression is eventually positive. We have obtained this expression from substituting the closed form of the update of this loop into the loop condition. Thus, this formula is valid if and only if x1, x2, x3 eventually witness non-termination of this loop. So, since eventually non-termination and non-termination are equivalent, non-termination is reducible to this theory. In this case here, if we set x1 to -4, x2 to 2, and x3 to 1, then alpha 1 is greater than 0, since x3 is 1. Thus, this loop does not terminate. So we have seen non-termination of TWN loops is reducible to this fragment. But this fragment is decidable for the real and real algebraic numbers and semi-decidable for the integers and the rationals. Thus, non-termination is decidable over the reals and real algebraic numbers and semi-decidable over the integers and the rationals. Now, decidability of non-termination is nothing else than decidability of termination. For completeness, I'd like to mention that if we just consider the restricted subclass of loops with only conjunctions in their condition, then an alternative proof for this result can also be obtained from combining these two existing works. But this only captures the case over the real and real algebraic numbers and not the case over the rationals and the integers, and also it does not capture the case where we have disjunctions in the loop condition. Now, what about non-TWN loops? For example, consider this loop. It's just a horrible loop. Please do not try to understand what it does. But agree with me that, for example, x1 depends on x3, x3 depends on x1, so we have a circular dependency. x3 depends non-linearly on itself, so we might even have this super exponential growth here. Still, I'd like to know, does this loop terminate over the integers? Now, these polynomials, they look so horrible since we have fixed the generators x1, x2, and x3 of this polynomial ring so far, and we have represented the polynomials with respect to these generators. So now let's just take different generators, y1, y2, and y3, and here I propose to take the ones which are obtained from the variables by multiplying with this invertible matrix. Then, if we transform the loop accordingly, we obtain this loop. And if we have a closer look, then this is exactly the loop which we have analyzed before, where the variables are just named y instead of x. Thus, termination of this loop over the integers, or more generally some ring S, can be reduced to termination of a TWN loop. Now, whether this is possible, so whether we can transform a loop into TWN form, is semi-decidable. For these transformable loops, then, termination is decidable over the reals and real algebraic numbers, and semi-decidable when the variables range over the integers and the rationals. Now let's consider the complexity of deciding termination for loops with a linear update, meaning the update is given by this form where A is a matrix and B is a vector. First of all, it turns out that having this addend here in the end does not increase expressiveness, so we ignore this. Now if A is triangular, then the loop is triangular. If A has only eigenvalues in the real algebraic numbers, then the Jordan form over the real algebraic numbers is a triangular matrix. Thus, this loop is always TWN transformable. This transformation can be done in polynomial time, and computing the closed forms is also possible in polynomial time. Thus, deciding termination is, if phi is linear, co-NP complete, since then deciding unsatisfiability of a linear arithmetic formula is co-NP complete. And if phi is non-linear, then it is for all R complete. For all R is the complexity class which contains all the problems whose decidability can be reduced to an universally quantified formula over real arithmetic terms. And for example, deciding whether an existentially formula is unsatisfiable is for all R complete, which leads to this result. What about general TWN loops? The picture for general TWN loops looks grim. The reason is as follows. Consider this TWN loop, x1 is set to x2 to the power of d, and so on, until xd minus 1 is also set to xd to the power of d, and xd is just multiplied by d, where d is the number of variables. Now the closed form is this vector, and it contains this tower of powers of d, whose logarithm grows stronger than any polynomial in d. Thus, we cannot compute the closed form by only using polynomial space, since we cannot represent it in polynomial space. But P space contains this complexity class, thus computing the closed forms is not possible in this complexity class, and thus our decision procedure cannot give a tight bound on the complexity here, since termination is for all R hard, but our procedure is not in for all R. Thus, so far, we do not know of any tight bound for deciding termination of TWN loops. To sum up, I have shown novel decidability results for termination of TWN loops. I showed how to handle certain non-TWN loops via a transformation. And I gave tight complexity results for linear update loops with real spectrum. In future work, we would of course like to generalize our decidability results to a wider class of loops. We would also like to handle complex eigenvalues in the tight complexity results and give tight complexity results for the general case. Thank you.